we try and get the kids trying to think through how could that have happened if it wasn't magic. How could you make that trick work? And then we actually teach them how to do the trick. So we both teach them how to do magic so they can go and do their own magic shows, and at the same time every magic trick has got some computer science and usually interdisciplinary computer science sort of linked to the trick of what's going on underneath. So I thought I'd start with one that's actually linked to my research. So I do research on human error, which is what a lot of this comes out of. So what I thought I'd do is a card trick, this is actually one of my favourite tricks, and I need another volunteer. So we've used up most people now. So who hasn't volunteered yet? Anybody who hasn't been out? Yes, okay. If you'd like to come out and be my volunteer, I'm going to need more volunteers. So some people are going to have to be twice. But basically, I want somebody who's close up. So this is close up magic. If you want to stand up, or just get yourself in a position where you can definitely see what I'm doing here. And you're basically here just to be the person who really is close up, so you can watch my sleeves and make sure there aren't any cards going up them or whatever. Basically, though, this is really a lesson in why you should never gamble, and certainly don't gamble with magicians or computer scientists. Okay, so the idea in a lot of games, one of the things people can do that actually casinos ban is card count. And the idea of card counting is just to kind of try and keep track of where cards that have appeared before have gone, and which ones have appeared and which ones haven't, and then use that to sort of beat the odds. So you can kind of have a discussion about probability sort of linked to this. But basically, the more information you have, the more chance you have of beating the odds. Okay. So in this game that we're going to sort of pretend to play a game, we're assuming that actually the aces are the things that matter. So whoever ends up with the most aces wins the game. Okay, and if you end up with all the aces, then you can't be beaten. Okay, and let's assume we've got the 4 aces that just happen to have ended up 1 in each pile in the previous game. What I'm going to do is just put 3 normal cards on each pile. So we've got hands of 4 here. So 4 cards with each person, and each person has an ace as their last card. And if we notice that, then what we can try and do is try and follow the aces and watch where the aces go. And that will help us know whether to gamble or not in the sort of later rounds. Okay, so you're the close-up person, so you've got to keep your eye on these aces and make sure you know where they are. And if you know where they are, then you end up winning. Is basically the idea. But they're at the bottom. They're every 4th card. Is the basic point. So basically, if the dealer picks the cards up now and doesn't shuffle, we can actually do better than just using probability to sort of beat the odds. We will know exactly where those aces go. So I'm going to make it easy for you. They're every 4th card, and what I'm going to do is just deal out 4 hands. So if I deal out 4 hands again, all the aces are actually going to end up together in the last pile because they're every 4th card. Yeah? See that? So let's actually do that. So we just deal them out. We go 1, 2, 3. And the 4th card is an ace. Yeah. So do you want to just turn that one over and show everybody that that card is actually the ace, and then leave it turned over? So no, leave it turned over, and then we keep going. So we go 1, 2, 3, and an ace. 1, 2, 3, and an ace. 1, 2, 3, and an ace. So that person's ended up with all the aces. Okay. And if we've been watching, then we know that, and so we know, basically not to gamble against them. That person will see they've got all the aces, and they'll just sort of throwing money in and try and kind of get as much money from everybody else as they can. The longer other people stay in, the better. Okay. So actually, can you just point to any 2 of the other 3 piles for me? So let's suppose those 2 people, maybe they were watching the aces, so they just drop out straight away. They decide there's no point staying in. And let's suppose this is my hand, and I decide I'm going to stay in. I know you've got the aces, so I ought to drop out, but that's your hand and you've got a perfect hand. You're just going to try and keep me in, throwing as much money in as possible, because you'll get it all, because you know you've got a perfect hand. In this game, you can actually swap one of your cards for somebody else's, so you're not going to want to do that. You'll skip on this step because you want to keep your aces, but I will at least take one of your aces, and I'll even give you a queen for it. But that's still going to be, you've got 3 aces and I've got 1, so you're still going to win 3-1. So really I should have dropped out long ago. But what I'm actually going to do is try and distract your attention and cheat. Okay? So what you've got to do is watch those aces, because I'm going to try and take them from you. And what you've got to do basically is not blink. Okay? I don't know, do you see Doctor Who around the world? So there's these monsters in the BBC TV series Doctor Who. If you blink, you basically turn to stone and everything goes wrong, basically, if you blink. It's a bit like this. You blink, I'm going to have fast enough reactions that I can steal those in the blink of your eye. Okay? And I'll try and make everybody blink, but it's you I'm focusing on here with this trick, really. Okay? So try not to blink, and don't, whatever you do, look away from those cards. Okay? You're very good. Most people look into my eyes at that point, but he's obviously very concentrated and good. It's going to be difficult, this. Let's see if I can make you blink. Okay, on the count of 3, 1, 2, you blinked. And while you were blinking, that allowed me to do my evil things, and I actually stole all your cards. Okay, because you did have a really good hand there. You had a perfect hand, and then you had 3 aces. But actually now you don't have any aces at all, because I've stolen all your cards, as I said, and you're left with no aces, and all that money you piled onto the table actually has gone to naught, because I'm the one with all the aces, and I'm the one who actually takes the money. And that's why you should not gamble with magicians or computer scientists. Okay, so thank you. And as I said, at this point, we actually get people to try and work out what's going on. Some people may have actually seen that. He was the one I was really trying to make sure didn't see it. So don't shout out what happened, but just put your hand up if you did actually see me take the cards and move them to the other side. No? Nobody saw that? No. Okay, so as I said, so what anybody got any ideas? How did I do it? Am I telling the truth? I've got such fast hands and I did really make you all blink. No? So anybody got any other ideas? Or when, if it wasn't then that I stole them, when did I steal them?
Did you just change the order?
Ah, so when did I change the order, do you think?
When?
But how is picked up this?
At the
You could know
beginning,
which.
because you put one in this side and the other one in the other side, so probably from the beginning.
Somewhere from the beginning, okay. You'll
Pick
say.
them up.
When
Okay.
you are sliding the card,
Yeah, but
the
then
top
how is
or the...
this?
Oh, so you think I've dealt something from the bottom, was it?
Bottom, the bottom,
No.
yeah.
Okay, so you've all got
I think it
theories.
was when,
Theory.
when you move this files in the corner, probably.
So you think it's when I moved those away, I did
That's
something.
why.
Okay, so the thing here is I'm a teacher and I'm not a magician really, so I'm not interested in leaving you baffled. I want you to learn so you can go and do this yourself. And it's actually really simple. So what I'm going to do, and you should never do this as a magician, I'm going to do it again, and this time you've got your theories so you can watch where you think is the place to watch it. And that's why you never do it a second time, normally with a trick. So watch really carefully this time, and I mean, same for you. It's all on the film. You can go back and watch the film presumably at some later point. So I'll do it faster this time. But 3 ordinary cards, and they're really all ordinary cards. Turn the aces over. The aces are at the bottom, and I'm not cheating yet. I can show you the aces are actually every 4th card. Not cheating yet. Not cheating yet. And I'll do that very carefully. You can see I'm not cheating. So we then deal the cards out. We go 1, 2, 3, and the 4th card is the ace. And turn that one over again and show everyone that that actually is the ace.
Oh no, we put it down.
So did everybody see that?
Yeah.
So what happened is I pointed with the top card, and then I got everybody to have their attention distracted by that. Actually, pointing is a really strong social signal. When you point, it's very difficult for people to not look where you're pointing. So I can just slip the card back to the bottom of the pile, and now the aces are the 3rd card away. So what's going on there? So again, this is where we get to the sort of interdisciplinary themes of this, and what's the science behind this? Well, actually, I'm drawing on cognitive science. Basically, magicians use a pretty deep understanding of the way people see the world to actually control the way you see the world. And actually, pointing is a strong social signal. When you point, people look at where you're pointing, and they're not then sort of looking at what you're doing. It also shows that you've got only one focus of attention, because actually the first time I did it quite close to where you were looking, and I was sort of pointing to the card, and what it shows is if your attention is in there, it's not actually even a few centimetres away to see what's going on there, even though it feels like you're seeing the whole room, the whole field of view. When your attention's focused, you're actually only focusing in one place, and you actually miss everything that's going on round about. Your brain's just filling in the detail. Okay? So actually it's already happened at this point, and so you can go into a bit more about the cognitive science of attention and so on there, but basically it's already happened. So when I'm doing 1, 2, 3 and an ace, I'm just reinforcing a lie basically, 1, 2, 3, 4 and an ace, and you sort of do that chant to reinforce that that's where the aces are. And again, you're sort of giving somebody the false mental model and trying to reinforce that false mental model. Mental models are something that are important to computer scientists as well. But it's already happened, so where are the aces now? Are the aces there?
No.
No, so where are the aces? The aces are already in the second pile. Oh, they're not. So where are the aces and why are they not there? Oh, yes. So where are the aces? They're not there. Actually, the aces are already all the way over here. Does anybody know why they ended up here this time?
How many times you pointed with the ace?
Yeah, exactly. So actually, I told you exactly what I was doing then, and then I did it 3 times. So I showed you the first time, and then I did it twice more. And that shows how powerful that is. And I don't know if any of you saw me do it the other times, but even when I've told you what I'm going to do, you still don't see it. And that's how strong that effect actually is. You know, and I'm not really a magician. I'm just an amateur magician that I'm doing it kind of for these shows. But you know, that's the kind of thing magicians are using, and it's really powerful. And actually, what I'm interested in is human error and the science and engineering around human error. And you know, when disasters happen, for example, if there's an aeroplane crashes, the pilot gets the blame. Or in an area I'm interested in, sort of with medical devices, if a nurse makes an error, the nurse gets the blame. But actually, there are situations where you can engineer a system, and magicians are engineering systems, but you can engineer a system where people are guaranteed to make a mistake. If you want them to engineer them like that, people don't try and do that in the real world, but if you're not very good at your job, you can end up accidentally engineering a system where somebody will make a mistake. And what magic shows show is it's not really down to a human being incompetent necessarily. I mean, it could be, but in general it could be, it's just, it was an accident waiting to happen. Okay? And this kind of trick shows that because everybody in the room made that mistake. And even when I trained you in the sense of I told you exactly what was happening, a few seconds later you were still missing it. So if you say, oh well, the solution to this kind of thing is to train people, you know, better training for the pilots who make mistakes, actually no, that on its own isn't going to solve the problem. Okay? So actually, if you'd like to sit down, thank you for volunteering. So what's that got to do with computer science? Well, computer scientists are engineering systems, and magicians need to have this understanding of perception, attention, and how cognition work, but so do computer scientists to make systems usable. And if they're safety-critical systems, like a flight deck or an infusion pump, this kind of thing that nurses might be using, you know, this kind of thing is pumping toxic drug potentially into somebody's arm, maybe a cancer treatment. You know, if you give 10 times too much, you might kill them instead of cure them. The nurses, though, have to program the interfaces. Now, let's suppose you're the nurse and you're programming this, and you've kind of typed in the number 12.5 milligrams per hour, and then you hit go, you know, button down at the bottom to hit go. What you want is your attention to be drawn to the screen before you hit go. Because actually, you haven't typed in 12.5, you've typed in 125. And if you don't realise that, you're giving somebody a 10 times overdose. And there are situations where nurses have gone to jail because they made a mistake like that, a person died, and the nurse was found negligent. But actually, I would say it's not the nurse's fault. That was an accident waiting to happen. Because in some cases, these devices are designed so that somebody's going to make that mistake. So there's, I forget where exactly, I think it was South America, somebody made a mistake where they typed in 2 decimal points in a row, realised they'd made that mistake and pressed delete to get rid of the second one, but didn't look to the screen to see what was happening, and actually the second decimal point had just been ignored silently. And so when they pressed delete, they actually got rid of the first decimal point as well. And they didn't notice, the person got an overdose and died, and they went to prison because they said they were negligent. But that really is an accident waiting to happen. Somebody was going to make that mistake. And if the blame has been put on the nurse, then it's not gone into fixing the system. And so the idea here is basically you've got to think about system solutions, and that's not about looking for blame. If you look for blame, chances are you won't fix the problem. Whereas you could go back and engineer the device. Actually, you'd be using the same kind of cognitive science that we were using there. What you need is to control the person's attention. Take their attention back to the screen. And if they did type multiple decimal points, maybe the screen should be flashing at them, not just silently ignoring it. And only when it's a dose that's within a sensible range should it allow you to press go. And the go button shouldn't be down at the bottom where your attention's drawn away from it. Maybe it should be up at the top. So what we can see here, again, it's one of these interdisciplinary stories where we're kind of starting, well, with magic, but that's allowing us to introduce ideas about cognitive science, and then we can go on to talking about actually engineering safety critical systems. And this is my research area, actually human-computer interaction. And that actually needs an understanding of humans as well as technology. Here's taking that same story going on a slightly different direction. So what we've got here is a picture. This was actually created by a mathematical model, so a sort of artificial intelligence, a mathematical model of the vision system, sort of taking theories about how our vision system works. Because as we've just seen, we don't see the world as a camera does. We're not taking a picture of everything. There's filtering going on, and shortcuts are being taken by your brain. Again, it's back to your brain following rules at some level or other. But so what's happening here is this mathematical model makes a prediction about an area of a picture, in this case that it thought your eye would be drawn to. And as it's flashing, it's making a change. So put your hand up if you can see the thing that's changing on this picture.
The number.
98.
Yeah, the number. So, and actually your eye, the model predicts, is drawn to that position because it's an area, in this case, of very high contrast. The fact that it's words also potentially semantically drawn, but even without the words, your eye is drawn to that area of the screen. And the model predicts that. Okay, so the model predicts that would be really easy to see. Okay, on this second one, don't shout out the answer, but this one is one that the model predicts is harder to see. Again, as it flashes, there's something changing. So rather than shout out, when you can see the change on this second one, just put your hand up, and we'll see how fast around the room it is before everybody sees it. Some people will see it more quickly than others, because it partly depends where your eye is drawn to at the beginning. Okay. So you ready? Put your hands up, but stay silent when you can see what's changing in this image. So as I said, the model says this is going to be harder for humans because the model is seeing the world and seeing this picture in the way you're seeing it. Anybody else seen it yet? 2 people so far. So clearly it is harder than the earlier one. And the reason for that, it's the same kind of cognitive science going on, but now a more detailed idea of what is it that draws your eye to things. And this model is a static model of the way that you see things, or the way your brain processes what's coming into your eyes. And it's all about small local effects of contrast. So your eye here tends to be drawn up into the middle, where there's lots of contrast. So shall I point out where the change is? So one more person's seen it. It's really big. It's a bigger area being changed. And when you can see it, it's really obvious. It's massive. How on earth can you not see the whole other side of a building appearing and disappearing? And again, that's showing how strong an effect this is. And your brain really is filtering lots out. And even when you're trying to see it, your eye is being drawn back. And what that shows is that underlying understanding of the biology of the vision system works. And what you've done is taken that understanding, turned it into a mathematical model. That mathematical model's been turned into a computer program, and then we can kind of do tests like this. The PhD student at Queen Mary who created this model, actually went a step further and went into art, because what he did is take that model and actually use it to do paintings. So what it does is takes a picture and sort of uses brush strokes, but what it does is in areas where it predicts your eye isn't drawn to, it puts really sort of big splashy brush strokes, and in this case it's obviously the sun your eye is drawn to. There it uses really fine brush strokes. So in areas where your eye is drawn to, it puts lots of detail, and areas where it's not drawn to, it splashes the paint on. And what you get is a fairly realistic, impressionistic style of painting. And maybe that's one of the techniques, or one of the things that's going on when impressionist painters are painting, that they're kind of putting detail in the area where they naturally think your eyes are going to be drawn to. But it gives you a way of going from biology all the way through to art, with a story about maths and computing along the way. and maybe it is something to do with the way humans paint, maybe it isn't, maybe it's a sort of style of its own. And this program has actually had its own art exhibition. In fact, I don't think it's made any money out of its art yet, but there's an app you can download actually that has kind of more of these examples. This is a last bit of magic. So you've actually got a version of this. So I'll do this quickly and I'll leave you to puzzle over it. So this is a version actually off the web. The one you've got is one that I drew for myself, and there's an algorithm behind how you draw these, which you can find on our website. But basically this is whether you can count, and this is sort of pulling in a bit of psychology and maths and turning it into a human-computer interaction story again. But I'll leave you puzzling about this perhaps. But what you've got to do is count how many people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people there. And so what we do is saw them in half and make one disappear. So now we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Oh, actually, I've made one appear. So we've got 13 people there. And before your eyes, they're all there. You can see everything going on. And now there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So which one's disappearing and where are they disappearing to? And you can actually do this same thing here. So it's sort of robots that you're counting. If you swap the top 2 layers round of this jigsaw, so it's just a physical jigsaw that fits together in 2 ways, you swap the top 2 pieces round, you'll find the same thing happens. One of those robots disappear. And I'll leave you to puzzle which one's disappearing and why, and when you want to know the answer you can go to our website and it explains exactly what's going on. But again, it's sort of talking about the limitations of our brain and the way we see the world, and you can get into human-computer interaction stories about what does that tell us about how we design computer systems to make them easy to use. Okay. How much time have we got? Sort of 5-10 minutes or so. Would you like more magic or move on to something else?
One more magic.
One more magic. Okay. So, what we'll do now is just a test of whether people are psychic. So this is more of a core computer science story behind this, but it's again mixing computer science with maths, and this is actually my other research area along with the human-computer interaction side of things. So again, I need a volunteer for this, so probably it'll have to be somebody who's been before. So here's somebody who believes he's psychic.
I know.
Got some kind of magical powers. So I don't know whether you've seen these kinds of cards before. These are what are called Zener cards, and they're actually used to, debunk people who claim they're psychic, I suppose. So one thing you do with them is they've got really obvious patterns, and you put two people in different rooms, and one of them looks at a random sequence of these cards and sort of thinks hard about the pattern they're looking at, and somebody in another room with no connection has to write down what the other person's thinking. So it's sort of seeing if people have got any kind of psychic powers, whatever way they're doing it, to sort of communicate. What I'm going to do here is a sort of one-person version of this. What we're going to do is muddle up these cards, and what you're basically going to do is see if you can use your magic powers or clairvoyance or whatever powers you've got to be left with 2 matching cards. Okay, but you're not going to look at the cards at all. So I've basically got 2 of each of these symbols in here. But let's mix them up a bit first. So just touch the back of one of the cards. So any card. And what I'll do is I'll just mix them in the points that you say. It's a bit tricky because they're big cards, but make sure I don't drop them all over the place. And we can keep going. Ooh, that one. Keep going through as long as you want until you think they're nicely mixed. So do you want to do one more? One more. That one. Okay. So we've mixed them up, and as I said, he's not going to see them at all. And what you've got to do is use your intuition from this point. So what we're going to do is just deal 5 cards. 1, 2, 3, 4, 5 cards, and that leaves 1, 2, 3, 4, 5 cards there. Okay. So what I'm going to do is give you 4 magic tokens to channel whatever psychic powers you've got. And what you can do is you can spread those tokens between the 2 piles, and I'll just do whatever the number of tokens sort of indicates. So you could do 4 and none, 2 and 2, 1 and 3, however you want to spread them. Okay, so you put 3 there and 1 there. So what that means is I do 1 move here, and I do 1, 2, 3 moves there, So just the number of tokens. So you're completely free choice direct to me, and then every time what we do is throw away the top 2 cards. So it doesn't matter what they are. What matters is you're trying to leave 2 cards that match at the end. Okay? So you're now 3 tokens, again, free choice, and I'll just do whatever you're telling me to do. So 2 and 1, so I do 1 move there, and I do 1, 2 moves there, and we throw away the top 2 cards. Okay. Yeah, just with 2. So both of them there. Okay. So we do 1, 2, and throw away the top 2 cards. This is where it gets critical. You could either put it there or put it there. If you get this wrong, I look stupid. So think hard about it. Are you sure?
No.
Don't want to ask the audience, change your mind again? You happy?
Yeah.
Okay, so he went for there, and that means I do 1 move there, which means it's those 2 we throw away, and it's these 2 that we're left with. Okay, so you had a completely free choice all the way through there. We did exactly the same each time, and I just did the number of moves you said. So you haven't seen the cards at all. How likely do you think that you are psychic that these 2 cards match? Do you think it's likely?
I'm lucky.
You think you're lucky? Okay, so you think it's quite likely that is a star. Okay, so if it is a star, round of applause. If it's not, a groan, I guess. So are you ready? Is he psychic? Does he have amazing magical powers? Yeah. So there you go. Of course, when you've found somebody that's got some magic powers, it's worth actually seeing if they've got more than they kind of might have thought. So let's actually look at the other cards, because maybe you've matched those 2 cards up, and you've matched those 2 cards, and you've matched those 2. In fact, you matched every single set of cards. And basically, you're amazing. You should stop denying your powers and start using them for the good of mankind, I think. So, back to the question we had before. How on earth do we do that? So, does he have amazing psychic powers? Should he start using them, or will he end up looking a bit foolish if he just starts going out into the world claiming to be Superman? Anybody got any ideas how that happens? No? Okay. We don't have a lot of time, so let me just sort of talk you through it. Actually, it's an algorithm. What do I mean by an algorithm? The same as we had with a piece of paper. It's guaranteed to work. So whatever happens, as long as we're following the kind of sequence of steps I did follow, and I didn't do any sleight of hand that time at all, I did no distraction. If you just follow that sequence of actions of dealing out 5 cards and so on, then you're guaranteed to have them all match up. That seems slightly miraculous, but actually it's true. And there's a few things that you just have to make sure. So the first thing is, let's think about what was going on at the beginning, because we shuffled them, didn't we? We mixed them up. Okay? So what I started with, as I said, is 2 sets of cards. And actually I started with them in the same order. So square, circle, plus wavy lines and star. So 2 sets the same, but we mixed them up. And how did we mix them up? He picked a card and we mixed them, and he picked a card and we mixed them, and he picked a card and we mixed them. Yeah. So they're nice and mixed up now, aren't they? Well, no, because actually they're 2 sets of cards in the same order. All I'm doing is cycling round 1 card at a time. I'm changing the start point, but the order's not actually changed. So even though we look like we were shuffling, we weren't. Okay? And then I deal out 5 cards. So I go 1, 2, 3, 4, 5. What have I just done to those? I've reversed their order. And then this set, I don't deal out, I just put down. And so now, whatever's at the bottom of that pile is at the top of that pile. And whatever's second from bottom there is second from top up here. Okay? Yeah. And that is a situation that guarantees, if I've got 4 tokens and there's 5 in each pile, let's look at the simple case. If I put all of the tokens in one place, what am I going to do? I'm going to do 1, 2, 3, 4, and bring the bottom card to the top to make it match to the top card there. If I did something different, like 2 and 2, say, I'm going to bring the 3rd card from the top here, which is a star, and here, that's also the 3rd card from the bottom which is a star. So whatever combination you do, you then throw away the top two, which are guaranteed to match. And what are we left with? Actually something that a computer scientist would call an invariant. Because what have we got now is the top card there is the bottom card. We're in exactly the same situation, but a smaller version of it. There's just 4 cards. So as long as I get rid of one of the tokens, it's now one less token, and exactly the same situation will happen again. Whatever the choice, even though it looks like we've got free choice and something different will happen, is guaranteed to end up the same. And actually what we've got there is the algorithm that I'm following, and actually it's in English again, but it's pretty close to a computer program version of it, using the same constructs of loops and sort of arithmetic and stuff going on in there as you would actually in a program. So it's another way of introducing ideas of what an algorithm is. But there's more to this than just the algorithm. To make this trick work, you actually, and all the other ones I've been showing you, you've actually got to put in more than just the algorithm. And the same goes for programs. And actually, well, there's 2 things. We'll get to the other part first. But how can we be sure something like that works? Well, what I just did is I gave you an argument. Essentially, I did a sort of informal version of a mathematical proof as to why that always works. And actually, that's something you can do with computer programs, with algorithms more generally. You don't have to just believe they'll work. You can prove that they work. And that's an area called program verification. What people actually do with programs is test them. So they don't do mathematical proofs generally, you just try it. And as a magician doing a trick, would I really want to stand up in front of an audience when I just tried it a couple of times and it seemed to work a couple of times? No, you want to be sure. And really for programs you want to be sure as well. And testing isn't good enough. How many times would I have to test that before I was absolutely sure it would always work? So actually you use some mixture of argument and mathematics and testing to actually check that algorithms work. So it's a way of introducing how maths and computer science sort of come together to be sure that your magic or your computer program or your computer hardware even works in all situations. But actually, as I was saying, it's about more than that, because it's not just the algorithm, it's the presentation as well. Magic needs methods and a presentation, and so does computer science. And that trick has this thing where you're actually trying to engineer more than it just working. You're trying to engineer delight into the system. So what we do is have this false ending where you think, oh great, applause, amazing, and you were sort of expecting that to happen probably, but then you give people what they expect and then you go further. And actually that's something, if you're getting into e-commerce sorts of things, you're engineering systems that give user satisfaction, user delight. You actually want to start engineering emotions in your system. So it's the opposite of our robot. Instead of the robot having emotions, we're trying to engineer a system that evokes emotions in people, more than just the functionality. So you want people to say that was a brilliant trick. You want people to love the hardware or the software, the program, the system that you've come up with. So you really do have to understand people, not just technology. Okay, I can keep going on forever here. There's a couple more things I can go through. Do you want more, or are you ready for a break and I'll stop and finish at that point? I've got to the end of my time, so I'm happy to stop if...
Just go ahead.
Keep going?
I just need to speak to 2 people, just if you don't mind. If
Okay.
you carry on, it's just a bit urgent. Okay.
Right.
No, carry on.
Carry on. Okay, so I'll do these last couple of things. I'll just give you a kind of idea of what's going on here. So here's another way you can start talking about the sort of link with computing and this time biology of evolution. So in this case, what we've got is actually creatures that people have drawn in a virtual world. So we've got this physics world called Soda Play, which actually allows you to draw drawings and they come to life. So I could show these people this at the end if they're really interested. But you can go further than that. Once you've drawn on the creature, you switch on the laws of physics, which is basically Newton's laws and a couple of others, and these creatures sort of come to life because basically each of the lines that you draw is a spring and each of the points is a mass, and so you've actually created a physical system. But you can then evolve these creatures, and so this is actually an evolved version of that. And what do we mean by evolve? Well, you take the creatures and you put them up against some kind of fitness test, and the ones that pass the fitness test are allowed to breed. And what do we mean by breeding? You take random mutations of them and then take those random mutations, they go up against the fitness test, and the ones that survive it breed, the best ones breed, and so on. And here, what we were doing for our fitness test was how fast are you over a flat course. And what you end up with is actually, from this nicely engineered thing at the beginning called the dainty walker, you end up with this thing that's actually got much more powerful back legs, weaker front legs, and actually it's sort of getting towards the way a cheetah is designed to be a fast creature, or maybe moving towards a kangaroo even, as you get this kind of really kind of weaker front leg. But there's a sort of interactive app that you can download to show this. So basically, you can play around with this. You download a race course. This time it's on on a slope. We've got our creature is that one racing against a hopping creature and a worm-like one and a walking one and so on. And actually, the thing we've engineered came last. It's not very good, but we can engineer a better one. And how do you change things? You can change the number of points, the number of lines, the amplitude of the energy boost it gets, and the frequency of the energy boost it gets. So, kind of amount of food and how often it gets food, essentially. And suddenly, it's still the same kind of round, rolling creature, but it's massively faster just by those simple engineering changes. But you can actually then go further. That's a human kind of trying to tweak them to make something faster. But we can now evolve this, and what we're doing is random mutations, random changes to the positions of these, and racing all the creatures that end up. When we find a faster creature, that goes to the next generation, and its children are the ones that are randomly mutated, and we end up with actually an even faster creature that's actually just come about from random change. And you could end up with something like this just starting from that original version. And what you can do here is sort of play around with this idea of just leave it for longer and longer, and eventually you start to see that it's harder and harder to find changes that make a difference. You can try doing it over different courses, so you can kind of take a creature and see, can you get something that can survive the drop? And when we do this in classes, usually somebody manages to evolve a creature that gets over the line by flying, by basically gliding and never touches the ground. But don't have a lot of time, I'll leave that as a cliffhanger. If you want to know who wins that race, again, this is something you can go and download. It's from the Soda Race site, so if you Google Soda Race, you'll find that. I won't go into that much longer. Okay, very last couple of things. So another sort of talk that we do is sort of looking at how you can use computing ideas sort of more generally, how it's not about technology. So I've been doing examples of computation without technology. This is actually where you're looking at a real problem. So we've got this sort of situation where we look at somebody with locked-in syndrome. So this is where you're totally paralysed and all you can do is blink one eyelid. Okay? So basically, somebody who has a stroke and they end up being able to see, hear and think but just can't communicate. So you basically a perfectly intelligent brain locked inside this useless body is what it amounts to. And it's been, in the UK at least, in the news quite a lot recently. Over the summer there was a sort of court case of somebody trying to be allowed to commit suicide because they thought, well, it just wasn't worth carrying on living. They didn't want to carry on living with this. On the other hand, there are some people who've ended up with locked-in syndrome who've sort of gone the opposite way. And Jean-Dominique Bauby was one, and you might have seen this. I seem to have lost the book. There we are. So he was the French editor-in-chief of Elle magazine, and he actually wrote a book about what it's like to have locked-in syndrome. And what comes across in this book is actually this amazing love for life, basically. But in there he describes how he does it. So we turned this actually into a story. So if you were a medic, there's obvious ways you would start thinking about how can we help with somebody with locked-in syndrome. But what we kind of do in this sort of story is ask, so what could a computer scientist do to help, or computer science thinking, this sort of idea of computational thinking. And the thing we ask about, sorry, I haven't put the slides I thought in here. So what we ask about is, how did you write this book? Because all he can do is blink one eyelid. He can't write, he can't talk. All he can do is see and hear and blink one eye. And actually he describes in the book how he does do it. He has a volunteer, somebody kind of sits in the room and he dictates to them, and the way he dictates is they actually go through the alphabet, they say A, B, C, D, E, F, G, and eventually he blinks and they write that letter down. So the book starts something along the lines of, what is it? Through the great curtain of a window, a one glow announces the break of day. So they had to communicate, he had to communicate T, they went A, B, C, D, E, F, G, H, I, J, K, up to T, wrote T down, start again, A, B, C, eventually they said H, he blinked and they wrote the H down. So what I'd do with a class at this point, I'd get you actually doing that, communicate a word to each other using that code, because it's essentially a code. And so what we'd end up with there is a really slow way of communicating, but you can communicate like that. And that's basically people with locked-in syndrome, that's their whole lives. Okay? But it's a very slow way of doing things. And you can actually start to ask how long does it take to communicate a book like this by doing what a computer scientist would call an efficiency analysis. So basically, we can count the number of letters in the book and ask on average how long does it take to ask each letter, work out what each letter is, or how much work, how many letters of the alphabet were read out. And on average it's 13 letters, because for every A it could be Z, for B it could be Y, and so on average you end up being, for each letter you would have asked on average 13 letters to communicate it. And you multiply that by the number of letters in the book, and that's how much work was taken to communicate the book. And you can start, if you try this, you'll see there are problems you've got to overcome, and actually trying it makes you start thinking about those problems. But you can actually come up with faster ways of doing that. And actually any computer scientist knows that actually 13 questions is too long. You can do it in 5. Because what we're doing there is something a computer scientist would call linear search, where you ask things, is it this, is it this, is it this? And so what I do at this point, again, I'll give you an idea, but I won't do this, but I would switch to playing the game of 20 questions. So this is where I think of a famous person, and you've got to try and work out who I'm thinking of, and I'll just answer yes or no. Okay, and that's the same as blinking or not blinking. And you've got 20 questions to work out any of a million, thousands of people that I might be thinking of. And actually you can do it really quickly. You know, so if I am thinking of a person, I can guarantee you would have got it in 20 questions. And you don't do it by asking, is it Nelson Mandela, is it Gandhi, is it Einstein, is it? You don't ask that sort of question. You ask questions like, are they male? Are they Asian? Are they alive? And all of those questions are a completely different sort of question. They're 50-50 questions. Whatever the answer, you rule out half of the possibilities. Okay? So, given that, you can actually get down from a million possibilities to one possibility, you know who it is, in only 20 questions, if they're all halving questions. And yet, with 26 letters of the alphabet, we're taking 13 questions to find out which letter of the alphabet it is. So, what we can do is map from one problem to the other, and you can basically take that same solution and apply it to this different problem of helping somebody with locked-in syndrome to communicate. They shouldn't be asking A, B, C, D, E. They should be asking basically which half of the alphabet is it in. And as long as they can blink easily, then you would get to any letter in only 5 questions. And so that's using computational thinking to actually help somebody, not multiplying by 13 to write this book, but multiplying by 5, and not on average in the worst case. So it's much faster and much better. And so essentially we'd improve the person's life. As long as actually what you did, I will finish at this point, as long as actually what you did is make sure you understood the problem. Because if it's hard for him to blink, then actually you made it 5 times harder, because you've got to blink 5 times to get to each letter of the alphabet, blinking yes, no, of which half of the alphabet. But what we're actually doing there is using computer science and saying, look, actually, without any technology there at all, computer science ideas can help somebody with a problem that's a very human problem of just communicating with other humans. And then you can start asking about technology of brain scanning and, you know, video systems that blink and so on. And so what we've got there is kind of now looking at real life stories, and again it's sort of mixing subject areas, sort of talking about how you help somebody with a disability, and you would think immediately technology, or you would think from a medical point of view, how you might help them, but actually you can come at it from a different angle. So we actually talk about our talks being serious fun. So there's a serious message behind all of them, but actually you still kind of give people an interesting fun time. And I've ended on the serious note there to kind of get across the idea that it isn't all about just fun, and the idea is about real problem solving in the real world, solving things for real people. But across all the things we do, we're trying to mix these interdisciplinary and integrate stories from different sciences and engineering with computing. And we're just using computing as this sort of central thing that kind of glues things together and getting across computing ideas, but actually trying to inspire people about science and engineering, that you can make a difference as a computer scientist, but maybe we've inspired you about biology, but understanding these computational thinking ideas is actually useful and important as a biologist or as an artist. You could do interesting things and so on. So, for serious interdisciplinary fun, this is my message. Actually, computer science is a good place to start. It's not about IT, it's about computation, and that's something that gives you lots of scope for lots of fun things. And if you want to know more, I've brought a bunch of handouts. So the magazines that we do, so there was the sort of 3 magazines I said, but there's an artificial intelligence booklet that we do that actually has a lot of the activities that the artificial intelligence ones that I was talking about there. We've got one on women in science, which is 60 pages of things that women have done with a computer science, electronic engineering focus. But again, it's interdisciplinary work. There's also, I hope there's one each of these. There's a magic book you can take. So if you want to do magic, there's a whole booklet full of magic tricks with computer science and other science stories that are behind them. And there's actually, if you go to the website, there's a lot more. There's another magic book as well. We have tricks that help explain medical tomography, for example. We have tricks that link to psychology. We have tricks that link to all sorts of things. And there's a whole magic show in there that you could do yourself, and they're all easy, because I'm not a magic magician, and if I can do them, anybody can. It just takes a little bit of practice to get the confidence and believe it. So, you saw, I was sure actually half the audience had seen when I slipped that card underneath, but actually, turns out they didn't. As long as you're sort of smooth and subtle with things like that, it just happens, and it's amazing how strong these effects actually are. You don't need a lot of skill. And one's like the algorithmic one, it's just follow the rules and it happens, whether you understand what's going on or not. And that's really what computer science is about, is creating systems that are all about rules, but rules are everywhere, as I hope we've seen. So if you want to find out more, pick up the magazines or go to our website, and the teleporting robot, you can play around with that, it will keep you amused on the plane home. When you get home, you can go and find out where the robot did actually go. But I'll leave you with that. I hope that was interesting, and I hope me talking for longer than was allocated wasn't too bad, but thank you very much.